This is our video for the section 3.3, determining if a function is linear. So you may want to take a quick minute and either reread this beginning or copy that down. Linear function is going to be something that is a straight line. We can write it in this form, y equals mx plus b. We're going to be seeing this a lot. And in this case, the y and the x are always going to stay variables. They'll always be y and x. Whereas the m and the b are what we call constants. They're just going to be a number. So for example, this is what that could look like when we talk about it being in that form. We've got y is y, x is x, and then these other two things are just numbers. So a couple things to notice, this mx means, of course, m times x. So when we're looking to determine whether something is in that form or not, we need to have something multiplied by x. And then we have plus b. This is okay that it's a minus because it could be plus -2. That means the same thing. So if this sign is a plus or a minus, that's okay. So when we talk about something being in the form, y equals mx plus b, it should look something like this. And we'll see a couple examples later where there may be a part of this missing. So for example, it could just be y equals 3x. That would be okay, because this could be like plus 0. But again, we'll see those examples in just a minute. Domains, discrete means only certain values make sense. And continuous means all inputs make sense. And again, we'll get into that a little bit more toward the end here. First two examples are pretty straightforward. If it's not a straight line, it is not a linear function. Okay, so any sort of curve at all is not linear. Even if it's just two straight lines, that's also going to be not linear. It has to be one continuous straight line. That is the only way that a linear function can be represented as a graph. Example 2, we can determine if it is a linear function by looking at these pairs of values. So remember, this would be like a coordinate, x comma y. That would be 3 comma 36. And then the next would be 6 comma 30. So these x and y values represent coordinates, and we can use this to determine if something is linear or not. And the way we do that is we look for a constant difference in the x and y values. So for example, just looking at the x values, using addition or subtraction, we want to say how far is it to the next number? Okay, how would we get from 3 to 6? You say, well, we would add 3. And then we do the same thing. Okay, so from 6 to 9, we would also add 3. From 9 to 12, we'd also add 3. And this is an example of a constant difference. We are adding 3 each time. Now, if this is a linear function, the same thing needs to happen in the y values. It doesn't have to be 3. It doesn't have to be the same number, but that difference has to be constant. So for example, what's happening here, we are minus 6. 30 to 24, again, minus 6. Again, minus 6. So yes, this is a function. It is a linear function because there is a constant difference in the x's and the y values. Constant difference in x's and y's. And it has to be addition or subtraction. It can't be multiplication. It is a constant difference. So let's look at the next one. 1 to 3.5, that's going to be plus 2.5. 3.5 to 6, again, plus 2.5, looking good. Plus 2.5. What happens when we go to the y values? 2 to 9, plus 7. 9 to 20, plus 11. plus 15. Okay, so it's constant for the x values, but not for the y values. No, this is not a linear function. Okay, it has to be constant difference for both x's and y's. Final way we can determine if something is a linear function is by looking at its equation. So for each of these, we'll go one by one here. I'm trying to determine if I can make it look like this, y equals mx plus b. And this first one is a good example of this is a linear function. We're missing this part, right? There is no x at all. There's no number being multiplied by x. But if we think about that, if this number was 0, then 0 times anything is 0. That would just go away. So really, if we want to talk about how we can write this in this form, it would look like this. 0x plus 3.8. So in this case, the 3.8 would be that b value that we're talking about. So yes, this is a linear function. Number 2, y equals the square root of x. So in this case, this is not okay. It has to be just x. Okay, we can have something times x. We cannot have the square root of x. So this is a no. And because the square root of x is not linear. Moving on. Again, we're looking for y equals something times x plus or minus something else. In this case, our x is up here. It's an exponent of 3. Can't have that either. Okay, it has to be just x. So this is a no. X value cannot be an exponent. Next, got y equals 2 divided by x. And now we've got a y, we've got an x, but this is not going to be okay either because this x is in the bottom of the fraction. We could change this into 2 times something, like we could get close. If we were going to try to rewrite this, this would be 2 times 1 over x, because that x is on the bottom, plus 0, but this is not okay. Again, the x value has to be in the top of a fraction, the y has to be in the top of the fraction. This is not a linear equation. No. X can't be in the denominator, which is the bottom of the fraction if you're not familiar with that term. Next, I hope your first thought was here that we should probably distribute this 6, and when we do, what do we get? Y equals 6x minus 6. Does this match our form? Absolutely, this is perfect. I've got some number times x plus something else, so 6 times x minus 6. Yes, this is linear. And finally, we could rearrange this a little bit. We always want to get it in that y equals. Okay, that's our first thing we'd want to do here. So if we take that and we add y to both sides, we would have x squared equals y, or y equals x squared, same thing. And again, this is not in our form. Our x value can't have any exponents. So since this 2 is up here, that tells us that this is a no. X value can't have exponents. Okay. All right, moving on to our final example. The linear function 15.95x represents the cost, y, in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. So it might be helpful to write this equation out and then just kind of think about what do your x and your y values represent here. It told us that y, the cost, y, in dollars, for x tickets. So this is the number of tickets. So basically, if I know if I know how many tickets we're buying, I multiply it by 15.95 and I get the total cost. And it's important to notice that customer can buy a maximum of 4 tickets. So find the domain, and is the domain discrete or continuous? So here's what we mean when we talk about discrete is tickets, we can't have like partial tickets. It only makes sense to sell whole tickets. And since a customer can only buy 4, our domain, our possible values are 1, 2, 3, or 4. That's the only number of tickets that somebody can buy. So again, the domain is discrete because the only whole numbers make sense, no fractions. When we graph this, we're just going to plug in a value for the domain. So we're going to say, like, when x is 1, what is the value of y? So again, our equation is y equals 15.95x. So when we let x equal 1 times, got caught somewhere between a 1 and an x, times 1, then y is 15.95. So when x is 1, y is 15.95. That is 1 point on our graph. When x is 2, we would have 2 times 15.95, which is just under 32. So this is just an estimated graph here. When x is 3, it would be just under 48. And when x is 4, it should be just under 64. And now we're not going to connect these lines because that would indicate that the graph is continuous, but it's not. Remember, this is what we mean by discrete. Only these 4 points, those are the only solutions in this case that make sense, since we're talking about tickets and there being a maximum of 4.